Welcome to the New York City Category Theory Seminar. Paolo Perrone is going to give a impromptu talk on categorical probability theory. Oh, I didn't make you shared your, hold on. Paolo, you're a co-host, go.
Okay, so, okay, can everybody see?
Perfect.
Okay, so yeah, thanks for coming to this talk. It's going to be about categorical probability, Markov categories, and the Finetti theorem. Okay, so first of all, what's the idea of categorical probability? Well, you probably know that a lot of fields of math are benefiting from tools from category theory, but probability is one of the fields where this is happening slower than in other fields. And there are some approaches to doing categorical, to doing probability with category theory. And one of the newest ones, maybe even the newest one, is the one that uses Markov categories, okay? Which is the one that I'm going to present today for the most part, okay? So let's jump right in, I would say. So what is a Markov category? So the basic idea is that, as usually in category theory, the importance is on the morphisms, okay? So we would like to say the Markov categories are intuitively categories of stochastic maps. In a sense that I'm about to make precise. Okay, so imagine if your prototypical categories is sets and functions, here you have to think of sets and functions with a random outcome, okay? So the result may depend on, for example, rolling a die. This is the idea. Okay, so more rigorously, so a Markov category C is, first of all, a monoidal categories. So we can use string diagrams, which are probably the main tool in the case of Markov categories, which is, first of all, semi-Cartesian. So the monoidal unit is the same thing as a terminal object, but the product is not necessarily the categorical product. Okay, so just for the unit. And then, such that every object is a comonoid. So a comonoid object is like a monoid, but the maps are dual. So we have maps which are, one is to the monoidal unit, and one is to twice itself, okay? And we call these maps the delete or discard map and the copy map. So the idea is that the map to the unit deletes whatever information we were having in X. You forget which state we're in. While the one that copies the state, well, copies the information, okay? Keep in mind, in sets with the Cartesian product, these are just the terminal, the map, the unique map to the terminal object, and the diagonal map, the one that maps little x into xx, okay? But the definition is not over. So we have these maps and we want these maps make X a commutative comonoid. And these maps let me say commute with the monadal structure. So commutative comonoid, you probably know the usual axioms. With the monadal structure, we need to spend a little bit more time. So I'm going to use string diagrams, and we're going to read them from the bottom to the top, a bit like in theoretical physics. So these maps are going to look like this. The delayed map is going to be from X to nothing. And I'll just draw a little dot to say we have forgotten X. The copy map would be a bifurcation that goes into X times X, okay? So for example, commutative comonoid says that, well, first of all, if you copy X and forget one of the two, that's the same as the identity. You see, this is co-unitality. Or for example, that if you copy twice, then it's the same thing as copying twice in the other way, okay? That's co-associativity, right? So there's only one way of copying, really. And the fact that it commutes with the monoidal structure tells us that, well, if you have X times Y, then what is the copy map of X times Y? Well, this has to be the same thing as starting with X and starting with Y. You first copy X and you copy Y, then you exchange these two using the braiding. Oh, I forgot to say symmetric monoidal category, sorry. So that we can do this and see now we're left with XY, XY, okay, which is X times Y, X times Y. That's what I meant. This is the definition of a Markov category. Let me also say that semi-Cartesian implies that the unit is terminal, and so there is only one way of forgetting your state, so to say. In other words, if you have any morphism f from X to Y, or let me write it in string diagram, for every morphism f from X to Y, then you can apply f and then forget the result. Or you can also just forget the result directly, because there's only one way of forgetting the state, right? These are maps from X to 1. And since 1 is terminal, there's only one such map. So these two are equal, okay? Those of you that are familiar with sister algebras may think of this as a normalization condition. And this is indeed the case. Since we want to do probability, this reflects the fact that we want to use measures who have total sum to 1, okay? If you're confused by this last remark, just imagine that there's simply one way of forgetting the statement, that's it, okay? And let's not make this quantitative. All right, so this is the definition. Are there any questions so far?
You're going to tell us what it has to do with probability, right?
Yes, I'll tell you in 1 second.
Okay, good.
Okay, so we are not requiring the copy map to be natural. So what does that mean? This, I claim this is exactly randomness, and I hope I'll be able to convince you. So first of all, definition. So a morphism F from X to Y is deterministic if and only if the following equation holds. So we can do the following thing. We can take X, copy its value, and then to both copies, apply the process F. Or we can take X, apply the process F, and then copy the result. Now, I'm saying that F is deterministic if and only if these two are equal. Now, first of all, why? Well, intuitively, what is a deterministic process as opposed to stochastic? A deterministic process is a process such that if you do it twice, you get the same result. You probably know there's this famous sentence, I think it's due to Einstein, that says, madness is doing the same thing twice and expecting different results. Now, I don't know if that's a good definition of madness, but for sure it's a good definition of randomness. Okay? So if you see, if F, so suppose, for example, that X is a number, okay? And it happens to be number 2. And F does the following, rolls the dice and sums the result of the die to 2. Then you see that here we may roll 2 and get 4, and here we may roll a 3 and get 5. On the other hand, here on the right, we roll only 1 die, okay? So maybe +1, and then these two are going to be equal, 3 and 3, okay? So if F has no die inside, then this thing is going to be equal, okay? Now, before I come to the example, let me just say one more thing.
So 1 second. So if it is natural, then it's deterministic.
Exactly. So yes, exactly. So the following are equivalent for a Markov category C. First one is every morphism is deterministic. Two, as you said, the copy map is natural. Three, C is Cartesian monoidal. So you can probably prove that the diagonal map in Cartesian monoidal categories is natural. So that's what's going on. Okay? So morally, Markov categories are, of course, rigorously are what I've just said. But intuitively, you can see them as are like Cartesian monoidal categories with randomness, are plus randomness. Or non-determinism, of course. So this is not necessarily quantitative, but like with this idea that copying is not natural, okay? More rigorously, since, I mean, it's supposed to be a math seminar, let me be a little bit more rigorous. More seriously, Cartesian monoidal categories are, and this one can be made precise, of course, are just Markov categories with determinism. Okay, this is rigorous, okay? But this is the intuitive explanation. All right, let's see some examples. Of course, every Cartesian monoidal category is an example, but somewhat trivially, because the interesting thing is not happening. Let's see some more.
Can we, in Hilbert space, the diagonal map is not defined, or is it defined? It's just not natural.
You're thinking of the no cloning,
theorem.
Thing.
Yeah. It's not a linear map. That's the problem. So it doesn't exist. I don't know if it's.
So if I remember correctly, the statement is that no natural non-zero map exists. But I don't know if one could still define one and make it. I have not checked. I'm pretty sure that Tobias has tried to do this. So if he comes, let's keep it in mind and ask him, because
we'll pester him next week. Yeah. Okay, go on. Sorry. Yeah.
Okay, so here's a first example: the category of stochastic matrices, which is called Fin-Stoch. So, what's a stochastic matrix? It's a matrix such as all the entries are non-negative and the rows sum to 1. So for example, this matrix let's maybe add one more line. This matrix can be seen as a transition matrix from a state of 4 elements, from a set of 4 elements to a set of 3 elements, okay? But it's you see, it's not just a function, it's a random function, because this goes here, but you see this one, well, this one goes here and here with probability 1/2 and 1/2, okay? So these are finite transitions which are allowed to be random. And well, these can be composed. It's the usual matrix product. So you know that for matrix product to be defined, the rows of the first matrix has to be equal to the columns of the second matrix. So objects are just natural numbers that keep track of the number of the rows. And morphisms are stochastic matrices. What are deterministic morphisms? Well, these are precisely the morphisms where this does not happen, okay? So these are, let's say, 0, 1 matrices. So where for each row, all elements are 0, except 1, which is then equal to 1, the number, okay? So all the rows are like this row, okay? That's a nice Markov category. Another example is Stoch. So it's like the one before, but not finite. So you probably know that. Let me first say matrix composition is, well, what is A composed B, the entry ik? Well, you probably know this is the same thing as sum over J of A, ij, B, jk, right? That's the usual matrix composition. Now, if you view this, so what is this 1/2, for example? That's the probability. So if we call this like, I don't know, A, B, C, and D, and these call X, Y, Z, then what is this 1/2? This 1/2 is the probability of getting Y if we are in B, right? We are here. What's the probability of ending up in here? Oh, you see 1/2. So these are conditional probabilities, okay? So this composition is basically saying, if we have this composition has a meaning of composing conditional probabilities in this way. That's the probability of some Z given some Y times the probability of some Y given some X. Sum over Y, and that's the probability of Z given X, okay? So this is the so-called Chapman Kolmogorov formula, well, the finite case, which tells us in particular that the randomness that B may have and the one that A may have are considered here independent. Okay, what is stock? Well, it's like this, but with an integral, okay? So maybe before we go a little bit and we start using measure theory, are there questions about this so far? Because conceptually, everything is already happening here. Okay, it seems not. So what is stock? Well, objects are measurable spaces. So let's avoid confusion, not measure spaces, measurable spaces. So a set and the sigma algebra. Not a measure, okay? Morphisms are they're usually called Markov kernels. And this is probably why this is called Markov categories, because this is the most prominent example, which are, well, what is a Markov kernel from X to Y? That's a map from, maybe let's call this sigma algebra of X to distinguish. So this is a map from, so this is X, sigma X, this is Y, sigma Y. This is a map from X times sigma Y to 0, 1. Okay? Such that now in its first argument, it's measurable. So for every measurable set of Y, K of placeholder A that goes just from X to 0, 1 is measurable. And in the second argument, it's a probability. So for every X, K of X placeholder that goes from the sigma algebra of Y to 0, 1 is a probability measure. Okay, so equivalently, that's a map from X to probability measures on Y for a certain sigma algebra. So if this is X and this is Y, instead of mapping a dot to a dot, imagine it maps a dot to some distribution, Y, Gaussian or whatever you want, okay? So just like before we had 1/2 and 1/2, here continuous distributions are allowed depending on the space, Gaussians and so on, all of them, okay? So for those of you that know something about categorical probability, it is a traditional Stoch is the same thing as the Kleisli category of the Giri monad. If this is suggestive to you, that's what Stoch is. If you don't know what the Giri monad is, don't worry. Okay?
So can I ask you a question? Is composition of morphisms obvious here?
No, that's an excellent question. No, it's not obvious at all. So I just said that it's kind of like this, but with integrals, but let's actually do that. So the idea we have said that a morphism is in this form, right? So how do we read this? So we have X and Y. And let's do again the drawing. And what is K? So K takes an element of X and a subset of Y. So K takes a point in here and a subset in here. And then the mapping tells us, if we're in X, what's the probability of ending up in that subset? Just this part, okay? So intuitively, it's K of XA is the probability that A has given X. All right. So now, how do we compose conditional probability? So if we have another one here, then, okay, for every measurable subset B of X, of Z, and for every X, well, okay, what is the probability of ending up in B given X? Let's make some space. So here we have for each point here, we will have another distribution in here. And for each one of these, we get another one, okay? And so we have to combine them using the same convex combination, so to say, that's prescribed by this yellow distribution. In rigor, this is the same thing as the probability of ending up in B if we were in Y. But then when? Well, then for what's the probability of ending up in Y? Well, that's prescribed by this map, okay? So using the measure prescribed by now K, and then integrating over Y. Okay, or if you want like this, integral over Y of P, well, how do we call this? K, no, sorry, H of Y of B times T K Y of X. Okay, so compare this with this. You see, it's kind of the same, except that one has sums and one has integrals. Okay, so that's the Chapman-Kolmogorov formula for the generic case.
And it's Kleisli composition in some sense.
Yes, it's a Kleisli composition of a special monad called the Giri monad. Yeah. Yes. And the integral, in case you're wondering where it comes from, that's the multiplication of the Giri monad. But, so we can maybe get a little bit into the Giri monad if we still have time at the end. Okay. So that's another example of Markov category, which is very close to what people actually do in in probability. Oh, I see now that Tobias has arrived, right?
Yeah, but I think you can go on. We can reschedule. We'll have both of you.
Ah, okay, okay.
I mean,
Right.
Tobias, you okay with that?
Yeah, absolutely. Please.
Great.
It sounds like the perfect stand-in.
Okay. Okay. So, anyways, Paolo, go on. Thank you, Tobias.
Oh yeah. Okay. So these are some examples of Markov categories, and there are several theorems of probability and statistics that have been proven just using Markov categories. So maybe I haven't done a little bit of given the credit to the people. So it looks like the first ideas of what we today call Markov categories were defined by Golubtsov. Was it in 2009, Tobias?
It was more like late 90s, early 2000, around
the
2000.
90s even, okay.
Yeah, yeah.
All right. Much later, Shaw and Jacobs have rediscovered and developed a little bit of these concepts again. And then Tobias Ritt has reestablished and given the current form of the theory of Markov categories. So what's the nice thing is that many theorems, like results of probability, can be proven using Markov categories. And also the proof is categorical. So essentially by manipulating strain diagrams. So to give some examples, there is a Fischer Neumann factorization theorem of statistics, which you find in the paper of, in case you want to see the paper, I think it's called a synthetic approach to Markov kernels and so on. If you Google this, you'll find it, okay? Other examples are the notion of stochastic dominance and theorems of comparison of statistical experiments. So, well, Sherman, Stein theorem. That's, Fritz et al. And I'm in here, I'm in et al. Mm-hmm. So one of the things that we are trying to figure out now is, what about some of the, let's say, flagship statements of probability theory? So what about the law of large numbers, for example? And all the statements that are related to that look a bit like the law of large numbers, like central limit theorem or Glivenko-Cantel theorem, or especially the Finetti. Okay, so since we're approaching the end of the hour, in the remaining time, if you want, I can speak a little bit about what the problem is. Okay, let me maybe also, before I go there, mention another result, which is like already going in the direction of the Finetti, which has been proven in terms of Markov category, which is the Hewitt-Savage 0-1 law. Okay. Now, I don't remember if this is 19 or 20, but it's the only paper by these two authors exactly, so you'll find it. Okay, so now let's try to see what the problem is. Okay, maybe does anybody have any questions so far?
No, and you started at 10 after, so you have time. Go do your thing. Unless Tobias, unless you want to make sure he doesn't do something. Okay.
No, that sounds great to me. So thank you for letting both of us speak. Yeah, I appreciate it.
Paolo, go on.
Thanks. Okay. Thank you. Thanks to both of them. And so what's the main idea? So the definitive theorem concerns with exchangeable random variables, okay? So let's maybe start with a little idea. So suppose we have a morphism in our Markov categories that goes into x times x, okay? So x times x may look like, I don't know, this space. This is x, and we can project into the component. So if we have, ooh, what's happening? If we have some measure here, then you can like flatten it into one component or the other component, okay? Of course, a priori, there's nothing that tells us that these two marginals, they're called, so these two projections or like push forwards of the projection are going to look the same. So maybe what we have here is something that's, for example, you know, very thin in one direction and very wide in the other one, so that this marginal will look like this, but this one will look like this, okay? Like imagine seeing an ellipse from above, and then the two sides are different, okay? I imagine now a Gaussian, a multivariate Gaussian that has that ellipse as the sigma surface. Okay, so this, well, sequence of two, let's say, is not exchangeable. What is an exchangeable sequence? An exchangeable sequence says that these two things have to look the same, okay? Not only that, but so what's the idea here? You see that if you take the diagonal, okay, the diagonal looks like this in this position. Then this picture is not symmetric under the diagonal, okay? So now, an exchangeable sequence is a sequence that for every two factors, we will have symmetry, like the first example I gave you. For example, if you put a circle here, okay? All right. So in rigor, let's do math. X times X times X, and so on. Let me denote this by X to the N. Okay, it's we're Markov categories, so this is not necessarily a Cartesian product, okay? And now, if we have a permutation, I forgot spelling. From the set of n elements to the set of n elements, this induces a permutation, induces a map here. All right. And now, An exchangeable sequence is something like this, but with an infinite product. So form the infinite product. Now, some of you may say, okay, I know what infinite Cartesian products are, but what are infinite monoidal products? I'll tell you in a second, okay? Let's say x to the infinity, let's say, okay? Permutations act in the first n components, all right? And a map from A to X to this infinite product is exchangeable if it is invariant for all permutation for all n, okay? All right, what is the infinite product? So you can find it in the Fritz and Richel's paper, and it's called Kolmogorov product. Because it kind of subsumes Kolmogorov's extension theorem, not as a result, but rather as a definition. So the idea is that we are in a semi-Cartesian monoidal category, okay? So we have this natural map from X to the unit. So for every other object, then we can do this map. Which is given by the map above times identity, right? Which is what we sometimes think of like the projection or marginals. And these are natural. So now, if you have a lot of products, as many as 3, then we can do like forget Z, we can forget Y, we can forget X, then we can forget here Y and Z, here we can. And all these diagrams will commute. Okay? So now, suppose that we take X equals Y equals Z. So we really have powers. If we have X tensor N, then there are a lot of maps X tensor N minus 1, which forget one component, the other component, and so on, okay? Which will be basically a big version of the diagram we have here, but now imagine it with N. And we can go on. There's X, N plus 1, and so on, all right?
So one question here.
Yes?
This starts to look a lot like a simplicial structure to me.
Yeah, it is, in this case, it's a particular simplicial structure. That is true.
Does it make sense to talk about the degeneracies with the copy map?
Let me see. I think it is a little bit more general because in a simplicial structure, you just take So no, okay, so in a simplicial structure, you would also need to have maps the other way around, like the degeneracy maps, something like that.
Yeah.
And we don't have that here.
Right, so this is semi-simplicial?
I think also not semi-simplicial because here we are not requiring the indexing maps to be monotone. So there's a little bit more maps. So I feel like it's not quite similar, like almost, but not quite. Okay.
Okay.
So yeah, so what I wanted to say is that we're going to have a diagram and this diagram is going to be filtered. What does it mean filtered? Well, roughly speaking means that if you have two objects in your diagram, then they're going to have a common cone over them. Okay, take now the limit of this filter diagram. Okay, or if you want, we know what finite products are. Then for infinite products, just take the limit, okay? And that's the Kolmogorov product. All right, let's also fix the notation. Before I was calling it x to the infinity, what we call it is actually x to the n of natural numbers, because there's many infinities, all right? So that's the notation that we want. All right, so now an exchangeable sequence is going to be a morphism from A to x to this big N, such that we have these permutations. Let's call this P. Well, this diagram has to commute. All right. All right. Now, given Q simply from A to X, like, so not on this huge product, but just on one variable, then we can obtain an exchangeable sequence very easily by just multiplying Q with itself a lot of times. Okay. So we can form Q to the N, which is how do you do that? Well, okay, this big N is a limit of the small n. And so it's sufficient to find maps into this small n. What map do we put here? Well, we apply our map Q. And then, wait, am I doing this right?
I think you want to copy first and then apply Q
Good
on
point.
each.
Yes, right. Yep. Again, okay. Very good, yes. And now we apply Q n times. Yep, thank you. Very good, thank you. So the idea is Q times Q times Q and so on, okay? These have the property of being independent. These are product probabilities whenever you fix A. Okay. Not every exchangeable sequence will be in this form. All right. Now, given the situation The Hewitt-Savage 0-1 law say that if we have an exchangeable sequence P, and if we have a deterministic morphism into some y, which is, I mean, I would like to say exchangeable tubes, like which is permutation invariant, so which makes this triangle commute. So you see, you could like run this diagram with whatever path you want. Then F composed with P is deterministic. Have I said something stupid? Yes, exchangeable sequence in the form, I say, star. Okay, all right. So crucially, not every exchangeable sequence is in this form, because the ones that are in this form, in some sense, are deterministic. In some sense. All right. So one may ask, what about all exchangeable sequence? And now the Finetti theorem says but now not categorical. Well, not categorical yet, I would say, says if P is exchangeable, then it is not quite in the form star, but it's a convex combination of the things that are in the form star. Then P is equal to integral over some space y of some distributions q depending on y with some measure d mu of y, where mu is a probability measure. I mean, let me stick to the notation. And all the qi are in the form star. Okay. So let me try to give a little analogy. So imagine a triangle, okay? Like a triangle, really a Euclidean triangle. Now, not every point of the triangle is in the corner, is X, Y, or Z. However, every point in here can be expressed as a barycenter of these 3 points, like as a convex combination of these. So for example, this point S can be written as, I don't know, 1/2 X plus 1/4 Y plus 1/4 Z, right? It's like a midpoint of them. Okay. So not every point is, of course, on the corners, but every point can be expressed as a convex combination of the corners, okay? Sum of some mu I xi, where the xi are x, y, z, and mu I are these coefficients. So what we're saying above is the same as this, but in infinite, okay? So we have an integral here. So not quite is every exchangeable measure just a product of measures, but it can be expressed as a complex combination of those, all right? And at least that's one of the forms of the definitive theorem. What would be the deterministic ones? So what are the ones that correspond to, in this analogy, to these points of the triangle? So what are the ones where this thing is a Dirac delta? Well, those are exactly the product ones, and the fact they are deterministic would recover the Hewitt-Sabat 0-1 law, which was here. Okay, so if in the form Q, we get something here that's deterministic. All right. Oh, do you see a line? Why is there a line? Do you see the line too? Okay, I don't know. Maybe like this. Okay, perfect. All right. Are there any questions so far?
What do you mean not categorical yet? In other words, are you now going to come into a categorical statement of it, or?
Oh no, it's just a very ambitious yet. We're working on it.
It has not been proven yet categorically.
No.
Ah.
I know it's very dangerous to say next time we will tell you what it is. I know. But no, I was afraid that if I said not categorical, it could have come across as it cannot be made categorical. Like, I think it can, but we still haven't done it, or we haven't been able so far. Okay. I think I should probably stop here. So thanks for bearing with me with this a little bit improvised talk. So have mercy if it was not as precise as you might have expected, but please, I'm still here. You can, if you have any questions, and of course, you may want to have questions for the original speaker too, that knows more than me about these things.
Well, we have, first of all, thank you very much. It was very nice. It was very clear. That's very good for an impromptu speech. That's for not preparing and without slides. Ray had a question. Ray, you're first. Go. You had a question for the chat. No, Ray, you're muted. Ray, you know you're not muted, but you're not going through. Okay, anyways, in the chat, let me just read what Ray wrote, okay?
Yes, sure. Maybe can people unmute themselves if they're not?
Anybody can unmute themselves. He's unmuted, but he's not talking. Anyways, he says, since you mentioned non-determinism, I was wondering if you know an example of such a category which is not random but non-deterministic, as say the terms are used in automaton theory.
Oh yeah, great questions. Yes, I do. So the easiest one that is in that form is take, let me say, the Kleisli category of the non-empty power set monad. This should be helpful for people that know monads. For people that do not know monads, take the category, it's the same one, I'm just saying it differently, where objects are sets, morphisms are full relations. So I mean, probably know that a function has for each x only one y. Relations are allowed to have more or none, okay? A full relation is the one that may have more but not none. So for each x, there is always at least some y, okay? As, let's say, as for every x in x, there exists a y in y, such that x is related to y, okay? So this, you see that a function like this, so if you're here, you may end up either here or here. So in this sense, this is non-deterministic, okay? But it's crucial that it always goes at least to one place because of normalization, because otherwise the discard map is not natural. Otherwise, the unit is not terminal, okay? But so this is a perfectly good Kleisli categories. And you may guess the deterministic morphisms are the ordinary functions, the ones that are just like this. Not necessarily continuous, of course, but like where there's never a duplication or anything like that, okay? But you can take more sophisticated examples. You can take topological spaces and closed sets as opposed to just subsets and so on. But like the idea is that you have a set, you have another set, and to each element you may map into many. And if this is deterministic, then you just map to one. Yeah, great question.
In non-determinism, you're allowed to go to the empty category, the empty subset. So it's not.
Yeah, it's a full non-determinism. So maybe for the sake of completion, I should also say, if you want to allow for example, the empty set, or more generally, if you want to say that forgetting is not the same as applying a function and then forgetting, which is what you get if you allow the empty set, then you don't have a Markov category, but you have what's called a CD category, which are for copy and delete category. So in the paper by Shaw and Jacobs, you can find it in detail, okay? And that's basically a Markov category without normalization. So you can do a lot of pretty much this, I would say all of the things you can do in Markov categories, you can also do them there. Of course, there's a little bit less, but morally speaking, it's kind of the same construction. And in that case, then you can really do non-determinism in the traditional sense. And you can also talk about zero measures and so on.
Very nice. Any other questions? Okay, so I'm going to stop the recording.
Okay.